Let's discuss an important topic in linear algebra: eigenvalues and eigenvector. Eigenvalues and eigenvectors. Okay, so first let's start with the basic equation. Let's first understand what does an eigenvalue means and what does an eigenvector mean, because this topic is quite important in various branches of engineering. Maybe it's mechanical engineering, or it has various applications in, like for example, in mechanical engineering, if you have a stress tensor, then the eigenvalues of the stress tensor means just like a stress matrix, and the eigenvalues basically represents the eigenvalues. Basically, if you happen to find out the eigenvalues of that stress matrix, which is 3 by 3 at a point, then those three eigenvalues represents basically the principal stress or the maximum normal stress at that point. So it has physical significance in various branches as well. So I gave an example. If the matrix happens to be a stress tensor, then the eigenvalues represent the principal stresses: maximum, intermediate, and the minimum. So you have three principal stresses, and therefore the three eigenvalues represents those, and the eigenvector represents the principal plane. So this is from the application point of view, but first let's understand how to find what is the meaning of eigenvalue, and then how do we find out eigenvalues, and then what do we mean by eigenvectors in a mathematical. So let's do a complete rigorous mathematical treatment. So if I take A to be a square matrix, and say if I have a vector x, so this is a matrix and this is a vector. So if this vector operates on this matrix such that the result is I get some multiple of the same, that is, if I multiply a square matrix with a vector, and if x happens to be in such a way that if I get the after multiplication some constant, so this is just a constant times the same vector. So it can happen, I mean, for every matrix A, there can be a vector x. When you multiply that matrix with a vector x, you may get some multiples of the vector. Okay, so the starting equation is this. Now if I just do a mathematical treatment of this, bring lambda this way, okay, which I can very well write in this way, and this I can again write this as lambda. Well, x can be written as Ix, where I is basically identity matrix and x is, so it's like Ix identity matrix. If you can, identity matrix we all know it is 1 0 0 0 1 0 0 0 1. Okay, so this matrix, when you multiply with any vector, you will get the vector, right? You will get the same vector. So I am just writing in that way. Now I can take, so by just the properties of multiplying, I can take a minus lambda I to be common, right, to 0. Okay, so this basically is a system of linear homogeneous simultaneous equations. So what we have learned in the solution of equations, so if you recall, this is basically a system of set of simultaneous linear equations which are homogeneous. Why homogeneous? Because the right hand side is 0, that's why it's homogeneous. Okay, so now for we know that for a non-trivial solution, so we know that for non-trivial, now trivial here means, the trivial solution here means x1 h2 till xn is 0. For non-trivial solution, that is x1 not equal to 0, h2 not equal to 0, something like that. Okay, because for trivial, now trivial, let me just define what is trivial here. So trivial will be h1, h2, h3, so on till hn is 0. Okay, but we are not looking for that. So we have already seen that when you have a homogeneous linear set of linear equations, for a non-trivial solution, your det of this a minus lambda I has to be 0. Okay, that is for x eigenvector. I mean, remember, okay, let's be cautious here. I am not defining anything. So let for any vector x to be a non-zero vector, that is its elements to be non-zero here, then I mean, when you solve this, say you can take A to be a 3 by 3 matrix. So this becomes basically 3 equations, simultaneous equations, and in 3 variables. And now when you solve this, the default is the trivial solution where x1, h2, h3 is 0. But what I'm saying is, for a non-trivial solution to happen, the rank has to be 2, right? Rank of that has to be 2, and the rank of both augmented matrix and the A matrix has to be 2. And rank has to be 2 means obviously the third order determinant should vary. I mean, the largest determinant should vanish, and that's what we have done here. The determinant is 0 for it to have a non-trivial solution. That is quite obvious from the solution of simultaneous equations which we have seen for homogeneous case. So now determinant has to be 0. So how do I find out that? Now say if A happens to be a matrix something like this: A1, A12, A13, A21, A22, A23, and then A31, A32, A33. This say A matrix, and therefore A is A matrix, and therefore A minus lambda I would be A11 minus lambda, right? Or okay, A12, because I is something like this. Lambda I would be something like this: lambda 0 0, basically multiplying identity matrix with some constant. Okay, and now if you subtract A minus lambda I, it will be something like this. So all the lambdas will be subtracted with the diagonal term. Sorry, there is no lambda here, only with the diagonal term. This will be there. Now det of this, if you set 0, okay, then basically you get a cubic equation in lambda. Okay, so now in the mathematics literature, this is called the characteristic equation, and the roots are called the eigen values. So this is just from the mathematical point of view. Application, as I told you, from the mechanical point of view I told you. So the roots are basically the eigenvalues. Okay, and this is basically called the characteristic equation, and the eigenvalues of matrix A, because everything what we are doing is on the matrix A. So of matrix A. So eigenvalues of matrix A. So that is the thing. And now when you just substitute back in this equation, when you substitute back everything, once you have found out lambda, substitute back in this equation, you can end up finding x. So that x corresponding to value of lambda which satisfies characteristic equation So that X is called the eigenvector. So this is just the definition of matrix okay. So this is just the definition of so we have seen how to find out eigenvalues, how to find out eigenvectors, and what is characteristic equation, that is nothing but that of A minus lambda I. So now let's just so here one important thing is that for every value of lambda, like say if A happens to be a square matrix, so the point to be noted here is that for every value of lambda, that is for every value of every eigenvalue there, okay, so when you solve for X, it gives the eigenvectors. So for every value of lambda you will get one eigenvector. That's what is the point. Okay, and there are a couple of points to be noted here, so let me just write down those. First point, the set of eigenvalues is called spectrum of A. So just if you have found out say A is a 3 by 3 matrix, so you will get the cubic equation for 3 by 3, and then that set would be is called spectrum, and the largest value out of the absolute values of eigenvalue is called spectral radius. Okay, so let me just write down largest. So these are just purely definitional. Largest of the absolute value of the eigenvalues is called spectral radius of A. Okay, and multiplying the eigenvector by a scalar or multiplying the matrix A gives the same result. So that's the point. And for a given eigenvalue there can be different eigenvectors, but so this is an important point. So for a given eigenvalue there can be different eigenvectors. This actually when we solve one example, this point will be clear. So next we will be solving one example problem. But for same eigenvector there can't be different eigenvalues. What it means is that for a given eigenvalues there can be different eigenvectors, which we'll see, because the equation, the set of simultaneous equations has infinite solution, as you all know, for non-trivial case. So then you have lot of options. For a given value of eigenvalue you can have different eigenvectors, but then the reverse is not true. So for the same eigenvector there can't be different eigenvalues. So we'll see all this, but let's first take an example. Okay, so this is just the definition here. Let's take an example at this point just to find out the eigenvalues and eigenvectors, and just whatever the basic concepts which we have introduced, let's be clear with that. Okay, so let's solve one problem here. Find the eigenvalue and the eigenvector of matrix which is given something like this. Okay, so you have a matrix for which we need to find out eigenvalue and eigenvector. Okay, so let's solve it. This is quite a simple problem, but whatever we have defined, let's understand it. So first thing is, in order to find out eigenvalues, the main equation is the characteristic equation which we have seen. It comes from Ax is equal to lambda x. So the characteristic equation of matrix A, basically the roots of that will give you the eigenvalues. So the characteristic equation is what? Mod A minus lambda, this is det A minus lambda I. So det A minus lambda I would be det of, we have seen the diagonal terms, you have to just multiply, you have to subtract lambda and then take the det. It's as simple as that. Now determinant, because it's a 2 by 2 matrix, so the determinant of this would be just AD minus BC. If you have something like this, A, B, C, D, okay, now the det of this would be just the cross multiplication, so AD minus BC for a 2D matrix. And for 3D you know how to find out, so which we have seen already. So now it will be 5 minus lambda into 2 minus lambda minus 1 into 4, 1 into this is just 4. Okay, so this is the det. So det comes out to be, if you just simplify this, 5 to 10 minus 5 lambda minus 2 lambda plus lambda square minus 4. So this value comes out to be lambda square minus 7 lambda plus 6 is equal to 0. Okay, and that's what you have to set. You have to set the characteristic equation to 0. This is the characteristic equation. So now the roots of this equation, would be this. You can just simply factorize. So lambda square minus 6 lambda minus 6 plus 6 is equal to 0. Okay, so the roots basically are the, let's factorize 1, 6. So the eigenvalues is 1 and 6. So these are the eigenvalues. Now corresponding to this, let's find out the eigenvector. So for the eigenvector, you have to again start from that A minus lambda I into x is equal to this equation. Okay, and from this, because from definition x is an eigenvector when you substitute the values of lambda in this. So now this becomes, if you just simplify, this becomes 5 minus lambda 4 1 2 minus lambda and x, let the elements of x be x1 and x2. Okay, 0. Okay, so this is the general equation. Now for lambda is equal to 1, okay, let's substitute it. For lambda is equal to 1, what will I get when I substitute this? I'll get 4 4 1 1 x1 x2 is equal to 0. So this is just a set of simultaneous equations which I can just expand it and write in this form. 4x1 plus 4x2 is equal to 0. X1 plus x2 is equal to 0. So basically these two, if you just divide the first equation with 4, it represents same equation. So let x2 be k and therefore the x1 will be minus k. So the eigenvectors are minus k and k. Okay, this is just a simple way to mention. Now most of the time what we do is we end up, so k is just a constant, so we end up, now k, because you know that the set of simultaneous equations for a homogeneous case, the non-trivial case, solutions are infinite. So that's why now for this lambda 1, the eigenvector is basically minus k and k. Okay, and k can take now values ranging, k is